Hello everyone. In this class, I am going to explain photoelectric effect and dual nature of matter and radiations with brief synopsis and some important problems for your CET exams. Within a 10 to 15 minutes, I would like to explain the short synopsis. Already all of you have studied in your theory classes. Here a photon means it is a packet or a bundle of energy. It is called photon. It is in the form of E is equal to h nu. Nu is equal to c divided by lambda. Here h is the Planck's constant, c is the speed of light, divided by lambda is the wavelength, and it has certain properties, but the two important properties are the kinetic mass of a photon is, it is in the form of E is equal to mc square, but the kinetic mass of a photon is m is equal to E divided by c square is equal to h divided by c into lambda. And another important property is the momentum of a photon is p is equal to E divided by c, or it is also equal to h divided by lambda. And the next important thing is the graphs related to the photoelectric effect. The first graph explains the effect of intensity of incident light on photoelectric current. Suppose if I consider for a given frequency and accelerating potential, for a given frequency and accelerating potential, the photoelectric current is directly proportional to the intensity of the incident radiation. So the number of photoelectrons per second is number of photoelectrons per second is, or the number of photoelectrons emitted per second is directly proportional to the intensity of the incident radiation. Here this is directly proportional to the intensity of the incident radiation. And the second graph is the effect of potential on photoelectric current. Here, suppose if the positive potential of the anode is increased, the photo current is also increases and it attains a maximum value. This maximum value of photoelectric current is called saturation current. Here the positive terminal of the anode is increase, photoelectric current is also increases, it attains a maximum value, that is called saturation current. If the negative potential, this is negative potential, the negative potential is, or the negative potential of the anode is increased, photo current is decreases and becomes zero for a particular negative potential. This is called cutoff potential. It is mathematically denoted by the symbol Vs or V0. And the third graph explains the effect of frequency of incident light on photoelectric current. Here for an light of suitable frequencies incident on a photosensitive material, it emits the electrons. Due to that electrons, certain current is produced in the circuit. That current is called photoelectric current. But here it does not depend on the frequency of incident light, because photoelectric current simply depends on the number of photoelectrons emitted and in turn on the number of photons. Here the I is directly proportional to n and inversely proportional to 1 divided by d square or r square. Here when the frequency of incident on stopping potential, the effect of frequency of incident light on the stopping potential, if the frequency of incident radiation is increased gradually, frequency of incident radiation is increased gradually, the kinetic energy of the liberated electrons also increases and consequently the stopping potential is increases. Here these are the important graphs related to the photoelectric effect. Then next concept is threshold frequency. Threshold frequency, work function, stopping potential, already all these definitions you have studied in your theory classes, but here the important definition is threshold frequency. Threshold frequency means it is the minimum frequency. It is the minimum frequency below which no photoelectric emission takes place. Here, the below which no photoelectric emission takes place. When you draw the graph between stopping potential and frequency, it does not pass through the origin. Here the graph starts their journey from this point below which there is no photoelectric emission takes place. It shows that there is a certain minimum value of frequency that is called threshold frequency below which no photoelectric emission takes place. It is not possible when the high intensity of incident light, or it depends on the nature of the metal. These are the important properties of graphs. And the next important concept is Einstein photoelectric equation. Already we have studied. This is the metal. When a photon is incident on this metal, this is the photon, it is in the form of E is equal to h nu. When this photon is incident on the surface of this metal, photon is incident on the surface of the metal. Here, this whole energy is incident on the surface of this metal. Here, this metal absorbs the energy from the incident photon. Some amount of energy is used to do the work function, and other amount of energy is used to increase the kinetic energy of electrons. According to the law of conservation of energy, you get E is equal to h nu plus work function plus maximum kinetic energy, or it is in the form of h nu naught plus half mv square maximum. This is the final equation. Half mv square maximum is equal to h into v minus v naught. This is the important formula for Einstein photoelectric equation. Then another important formula in this topic is that is de Broglie wavelength, the wave associated with moving material particles. According to that de Broglie, here the particle is associated with the wave. You know this equation, lambda is equal to h divided by mv. According to that quantum theory, energy of the photon is E is equal to h nu or hc divided by lambda, and another formula is E is equal to mc square. Using these two equations, you get lambda is equal to h divided by mc, or lambda is equal to h divided by p. Here p is equal to m into c. It is the momentum of a photon. Or suppose if you express this equation in the form of material particles of mass m moving with the velocity v, then the equation becomes lambda is equal to h divided by mv, which is the expression for de Broglie wavelength. With this brief synopsis, now I would like to solve some more problems or important problems on this topic. Certain important formulas are there in this topic. They are energy of a photon E is equal to h nu, nu equal to c by lambda, or for n number of photon, I can write this equation E is equal to nh nu or nhc divided by lambda. And the second formula is the maximum kinetic energy is equal to E into Vs. This is stopping potential. Also, you can write this equation V naught half mv square maximum, or from using Einstein photoelectric equation, EVS is equal to h nu minus h nu naught, or hc divided by lambda minus hc divided by lambda naught. Here, the first problem is if the intensity of the radiation incident on a photocell and a light of suitable frequencies incident on a photosensitive material. The intensity of radiation incident on a photocell is increased 4 times, then number of photoelectrons and the kinetic energy of photoelectrons emitted becomes. The option A is 4 times and doubled, B is doubled and remains unchanged, C is remains unchanged and doubled, D is 4 times and remains unchanged. But here, according to the Einstein equation, the number of photoelectrons emitted is directly proportional to the intensity of incident radiation. You know the first graph. Here, you know this graph. Here, this is the graph. The number of photoelectrons The number of photoelectrons emitted directly proportional to the number of photoelectrons emitted directly proportional to the intensity of the incident radiation. Here you know that formula, the maximum kinetic energy Ke maximum is equal to h nu minus h nu naught. Here kinetic energy does not depends on the n term. Kinetic energy does not depend on does not depend on n, and this kinetic energy does not depend on n. If the intensity of the radiation incident on the photocell is increased 4 times, then the number of photoelectrons and kinetic energy of the photoelectron becomes also 4 times but remains unchanged. Here the option 4 D is the right answer. I is directly proportional to n and kinetic energy does not depend on n. Option D is the right answer. And the second question is, light of two different frequencies whose photons have energies 1 and 2.5 electron volt respectively successively illuminate a metal whose work function is 0.5 electron volt. Work function means the minimum energy required to liberate the electron from the metal surface is called work function. Now the ratio of maximum speeds of the emitted electron will be, here we know the formula, kinetic energy, that is the kinetic energy half mv square. Half mv square means it is the equation of kinetic energy. This kinetic energy equation is equal to, from using Einstein equation, half mv square is equal to E minus W. Kinetic energy is equal to E minus W. E here, E this is indicates photo energy, or here light of two different frequencies whose photons have energies 1 and 2.5 electron volt. For the first kinetic energy, this is Ke1. Ke1 is equal to 1 minus the photo energy is 1 minus the work function is 0.5. You get the answer 0.5 electron volt. And for the second kinetic energy, here for the second kinetic energy Ke2 is, it is 2.5 minus 0.5, you get 2 electron volt. Now I have to find the ratio of the maximum speed of the electrons will be, here dividing these two equations, half mv1 square divided by half mv2 square is equal to, that is 0.5 divided by 2. 1 by 2m get cancelled. Here you get v1 square divided by v2 square is equal to 0.5 divided by 2. v1 square divided by v2 square is equal to 0.5 divided by 2, that is equal to 1 divided by 4. But here they have asked the ratio of the maximum speed of the emitted electrons will be, that is v1 divided by v2 is equal to a root of 1 divided by 4. Now you get the result 1 by 2. The option C is the right answer. And then next, here the option C is the right answer. The third problem, according to Einstein photoelectric equation, the plot of kinetic energy of the emitted photoelectron from a metal versus frequency of the incident radiation gives a straight line whose slope already I have discussed in the synopsis. The relation between the kinetic energy of the photoelectrons from a metal versus frequency here. But according to Einstein photoelectric equation, we know the formula h nu is equal to work function plus kinetic energy. But here the kinetic energy is equal to h nu minus work function. Here compare this equation with the straight line graph, that is y is equal to here y is equal to mx plus c. Here slope is equal to m equal to h, which is Planck's constant, and it is same for all the metals and independent of intensity of radiation. Here m is equal to h, then first option is depends on nature of metal used, second option is depends on intensity of radiation, third option is depends on both intensity of radiation and nature of metal use, and option D is it is same for all the metals and independent of intensity of radiation. Yes, this option is right. It is same for all the metals and independent of the intensity of radiation. And the fourth problem is light of frequency 1.5 times. Light of frequency 1.5 times the threshold frequency is incident on a photosensitive material. Photoelectric current is emitted. If the frequency of light is halved, the intensity is doubled, then the photoelectric current becomes. Here, when the light of frequency is 1.5 times the threshold frequency. Threshold frequency is incident on that photosensitive material. When the frequency of incident light is halved, its original value is 1.5 volt, but it becomes less than the threshold value. In that case, no photoelectric emission takes place. No photoelectrons are emitted. Then photoelectric current becomes zero. Here initially it has the value light of frequency 1.5 times the threshold frequency, but if the photoelectric current is emitted, if the frequency is halved, then the intensity is double. But here the photoelectric current is directly proportional to number of electrons. The intensity, it is independent value. Now the exact answer is option D, 0 times the original. And then next, fifth question. Here the kinetic energy of electron is E, and the incident light has wavelength lambda. To increase the kinetic energy to 2E, then the incident light must have wavelength lambda dash. According to the Einstein equation, we know the formula E is equal to hc divided by lambda minus work function. This is equation number 1. But when we increase the kinetic energy to 2E, now we get the formula, that is 2E is equal to h into c divided by lambda dash minus work function. That's equation number 2. Now here compare this equation. 2E is equal to hc divided by lambda dash minus hc divided by lambda. In this case E plus, this is E plus hc divided by lambda is equal to hc divided by lambda dash, or here lambda dash is equal to hc lambda divided by E plus hc. This is the desired equation. The option C is the right answer. Here Option C is the right answer. Next question is question number 6. A photo cell is illuminated by a small bright source placed 1 meter away, and the same source of light is placed 1.2 meter away. The number of electrons emitted by photocathode. Number of electrons emitted by the photocathode. Here we know the formula. I is inversely proportional to 1 by r square, and or I is directly proportional to n. When distance becomes half, intensity becomes 4 times. Hence, no electrons increases by a factor of 4. No electrons increase by a factor of 4 because it is placed by 1 by 2 times r square. Then it is 1 by 4 times. No factor or no electrons increases by a factor of 4 times. Option D is the right answer. I is directly proportional to n and I is inversely proportional to 1 by d square. And then next question is, when a light of wavelength 300 nanometer falls on a photoelectric emitter, photoelectrons are liberated. For another emitter, light of wavelength 600 nanometer is sufficient for liberating electrons. The ratio of work function of the two emitter. The ratio of work function of the two emitter. Here the lambda 1 is 300 nanometer and lambda 2 is 600 nanometer. The relation between work function and their wavelength is, that is, inversely proportional. You know the formula. W is inversely proportional to their wavelength. Now I can write this new equation. W1 divided by W2 is equal to lambda 2 divided by lambda 1. Here the lambda 2 is 600 nanometer. Lambda 1 is 300 nanometer. 6 divided by 3 is, that is, 2 divided by 1. Now that is 2 is to 1. The ratio of work function of two emitter is 2 is to 1. Next question is question number 8. The photoelectric cutoff voltage in a certain experiment is, in certain experiment photoelectric cutoff voltage is 1.5 volt. The maximum kinetic energy of photoelectrons emitted is, here the given value is, that is V naught. V naught is equal to 1.5 volt. But the kinetic energy is equal to formula E into V naught. E into V naught. Now you get the equation. 1.6 into 10 to the power of minus 19 into 1.5 expressed in terms of electron volt. The SI unit of kinetic energy is joule. Now that is 1.6 into 10 to the power of minus 19. Cancel these two values. Again you get the same value, that is 1.5 electron volt. The option B is the right answer. Next question. The question number 9. The energy flux of sunlight reaching the surface of the earth is 1.388 into 10 to the power of 3 Weber per meter square. How many photons nearly per square meter are incident on earth per second? Assume that photons in the sunlight have an average wavelength of 550 nanometer. Here, energy flux of sunlight reaching the surface of the earth is 1.388 into 10 to the power of 3 Weber per meter square. That is the energy. E is equal to hc divided by lambda, or that is equal to number of photons. And how many photons per square meter are incident on the earth per second? Assume that here the sunlight have an average wavelength, that is lambda value. Lambda is equal to 550 into 10 to the power of minus 9 meter. You know the formula for n terms, that is E is equal to n into E is equal to, here E is equal to n hc E is equal to NHC divided by lambda. E is equal to NHC divided by lambda. But here E is equal to HC divided by lambda is equal to N. When you are substituting the Planck's constant, velocity of light and wavelength value, you get the option A is the right answer. It is a very lengthy problem. Try to solve yourself. Substitute the Planck's constant H value 6.6 into 10 to the power of minus 34 and C 3 into 10 to the power of 8 divided by lambda, that is 550 nanometer. 550 into 10 to the power of minus 9. You get the option A is the right answer. And then question number 10. The threshold frequency. The threshold frequency of a metal is F0 and light of frequency 4 F0 is incident on the metal. The maximum kinetic energy of maximum kinetic energy of emitted photoelectrons. Again, from using the Einstein equation, here it is E maximum. Here E maximum is equal to h nu minus h nu naught. Here this h nu is energy of photon, that is F0, and this is nu naught, this is threshold frequency, that is 4 into F0. Now reconstruct this formula. The maximum kinetic energy is equal to h into the maximum kinetic energy h into, here this is F0. Now substitute the F0 value, that is the kinetic energy when a light of frequency 4 F0, h into 4 F0 and minus here h into F0. Take the h value outside, you get 4 F0 minus F0. Here 4 F0 minus F0 is, that is 3 F0. Now h into 3 F0, or it is 3h into F0. The option D is the right answer. And the next question is question number 11. In photoelectric effect, the photoelectric current does not depend on photon frequency but only intensity of incident beam. Option B is depends on both on intensity and frequency of incident beam. Option C increases when frequency of incident photons increases, and option D is here. In photoelectric effect, photoelectric current, you know the first graph here. The first graph is that is when you draw the photoelectric current versus intensity, you get the graph like this. Here the photoelectric effect, the photoelectric current does not depend on the frequency but only on the intensity of incident beam. Here the photoelectric current is depend on the intensity of the beam. Photoelectric current depend on intensity of the beam. The option A is the right answer. And then the question number 12. In a photoelectric effect, when photons of energy h nu fall on a photosensitive surface of work function h nu naught with nu is greater than nu naught, electrons are emitted from the metallic surface with a kinetic energy if it is only possible. Here this is the metal surface and a photon is incident on this metal surface. Here photon, it is in the form of h nu. It absorbs the energy and it liberates the electrons. some amount of energy is used to do the work function and other amount of energy is used to increase the kinetic energy of the electron. You know this form. But here in this problem, when photons of energy h nu, this is the photons of energy h nu, this energy is fall on a photosensitive surface of work function h nu naught. Nu is greater than nu naught. Then only electrons are liberated, permitted from the metallic surface. If it is possible only to show that here all these ejected electrons have same kinetic energy equal to h nu minus h nu naught? No. The ejected electrons have a distribution of kinetic energy. The ejected electrons have the distribution of kinetic energy, that is h nu minus h nu naught. Here the option B is the right answer. Next question is question number 13. A photosensitive plate is irradiated from a distance of 1 meter. The photoelectric current is 0.1 ampere. Photosensitive plate is irradiated from a distance of 1 meter. The photoelectric current is 0.1 ampere. If the source of radiation is brought near to a distance of 502 centimeter, the photoelectric current will be. Here also from using the same formula, here I is inversely proportional to 1 by d square. Already I have discussed one problem. Here try to solve yourself, easily you get the answer. The option C is right. And next question is, in a photoemissive cell with exciting wavelength lambda, the fastest electron has a speed v if the exciting wavelength is changed to 3 lambda by 4. In a photoemissive cell with exciting wavelength is lambda, that is moving with the speed v. If another wavelength is that wavelength, initially the wavelength lambda is moving with the speed v and the exciting wavelength is changed to lambda to 3 lambda by 4. Now the speed of the fastest emitted electron will be. Now how to find the v dash value? Find the v dash value. Here the photoemissive cell with exciting wavelength lambda, it is energy E is equal to here the work function plus half mv square maximum. You know this form. But here we have to find the maximum speed, that is V maximum is equal to 2E divided by m minus 2W naught divided by m, because here E is equal to hc divided by lambda. Now I change this lambda to 3 lambda divided by 4. Lambda to 3 lambda divided by 4. Here the E is inversely proportional to lambda and it is equal to E dash, that is 4 by 3 times of E. From using the maximum speed equation, that is v dash is equal to root of 2E dash divided by m minus 2W naught divided by m. Then v dash is equal to root of, that is 2 into 4 by 3 times of E divided by m minus 2W naught divided by m. Here, and this wavelength is changed from lambda to 3 lambda divided by 4. Then v dash is equal to, you get 4 by 3 times the power of 1 by 2 into root of, that is 2e divided by m minus 2w naught divided by m into 4 by 3 1 by 2. Here v dash is greater than 4 by 3 whole to the power of 1 by into v. V dash is greater than 4 by 3 whole to the power of 1 by 2 into v. Here the option D, more than v whole to the power of 4 by 3. Option D is the right answer. And the next concept, now I will move to the problems on de Broglie wavelength. You know the formula de Broglie wavelength, lambda is equal to h divided by mv, and energy of the photon E is equal to mc square. Here the de Broglie wavelength lambda is equal to h by phi is equal to h divided by mv, or mv, it is momentum. Now this momentum equation you can write in this form, lambda divided by h divided by root of 2m into ek. The de Broglie wavelength, it is in terms of accelerated of an electron with the potential difference of phi, that is lambda is equal to h divided by root of 2m into e into v. You get this equation here, so that the de Broglie wavelength of an acceleration electron through a potential difference of phi, you know the standard value, that is 12.27 divided by root v angstrom. Here that is now the question is, what is the de Broglie wavelength of an alpha particle? The de Broglie wavelength of an alpha particle accelerated through a potential difference of phi. Here we know that formula, that is lambda is equal to h by p. Lambda is equal to h by p, then h divided by m into v. I can write this in the form of kinetic energy, that is h divided by root of 2m into kinetic energy. Here momentum p is equal to root of 2m into k, and energy, it is E is equal to q into v. But here the alpha particle is equal to, that is 2he4. Alpha particle is equal to 2he4. Now I can write the formula, that is here the lambda is equal to h divided by root of 2m. Root of 2m. Yes, the formula is there. Lambda is equal to h divided by root of 2m. But instead of this kinetic energy Ek, now I write this formula, that is qv, h divided by 2m into q into v. Lambda is equal to h divided by root of 2m into q into v. You know the value of lambda, that is Planck's constant, 6.626. Here 6.626 into 10 to the power of minus 34 divided by root of 2 into the mass of the alpha particle. Mass of the alpha particle. Here how to find the mass of the alpha particle? Mass of the alpha particle, it has mass 4 into, convert it into kg, that is 1.67 into 10 to the power of minus 27 into energy 1.6 into 10 to the power of minus 19 charge into v. Here when you are substituting the values, lambda is equal to 6.626 into 10 to the power of minus 34 divided by root of 2 into 4 into 1.6 into 10 to the power of minus 27 into 1.6 into 10 to the power of minus 19 into v. Here you get lambda is equal to 6.626 into 10 to the power of minus 34 divided by, here take this value outside, that is 1.6. Now root, here root, that is, now here 2 into 4. 2 into 4 is 8. 2 into 4 is 8. 8 into 2. Here 2 क्यों 8 into 4 is 16. That is 16 into 10 to the power of minus 46. It is equal to 6.626 into 10 to the power of minus 34 divided by 1.6 into 4 into 10 to the power of minus 23 into root v. Finally, we get the answer lambda is equal to 1.01 into 10 to the power of 11 divided by root v. But we can write this equation 0.101 into 10 to the power of minus 10 divided by root v. 10 to the power of minus 10, it is in the form of angstrom. Then you get lambda is equal to 0.101 divided by root v, 10 to the power of minus 10, that is angstrom. Here option C is the right answer. Third example is, next example, if the kinetic energy of free electron doubles, its de Broglie wavelength changes by the factor. Kinetic energy of a free electron doubles, its de Broglie wavelength changes by the factor. Here the kinetic energy is K. Kinetic energy is equal to P square divided by 2m. You know this form. Or P is equal to root of 2m into K. Lambda is equal to H divided by P. When you are squaring these equations, you get lambda 1 divided by lambda 2 is equal to P2 divided by P1. P2 divided by P1. The relation between wavelength and momentum is inversely proportional. That's why I write this equation lambda 1 divided by lambda 2 is equal to P2 divided by P1. P2 divided by P1, that is equal to, here P is equal to root of 2m into K. Now can write this K2 m2 into 2 divided by K1 m into 2. Here you get is equal to root of K2 divided by K1 is equal to root of 2K divided by K, that is lambda. Lambda 1 is lambda. Lambda divided by lambda 2 is equal to root of 2, or lambda 2 is equal to lambda divided by root 2. Here the option A is the right answer. And then next question is the de Broglie wavelength of an electron. The de Broglie wavelength of an electron with a kinetic energy of 400 electron volt. The de Broglie wavelength, here de Broglie wavelength, that is lambda is equal to h divided by root of 2m into E. Substitute the values here. 6.626 into 10 to the power of minus 34 divided by root of 2 into, here the mass of the electron. Mass of the electron is 9.1 into 10 to the power of minus 31 kg into 400 electron volt, that is 400 into 1.6 into 10 to the power of minus 19. Here when you are calculating this value, you get lambda is equal to 0.6139 into 10 to the power of minus 10 meter, or 0.6139 angstrom. 0.6139 angstrom. The option A is the right answer. And the question number 5. Question number 5 is a particle of mass m at rest decays into two particles of mass m1 and m2 having non-zero velocities. The ratio of de Broglie wavelength. Now I repeat that question. A particle of mass m. A particle of mass m at rest decays into two particles of mass m1 and m2 having non-zero velocities. The ratio of their de Broglie wavelength is here by using law of conservation of momentum. By using the law of conservation of momentum, that is here it is mv is equal to m1 v1 plus m2 v2. This is equation number 1. But here m is initially at rest, then the velocity of that particle is 0. Now you can write the equation number 1 as m1 v1 is equal to minus m2 v2. It means that the magnitude of momentum of both the masses are equal to p1 is equal to p2. From de Broglie hypothesis, we know the equation lambda 1 is equal to h divided by p1 and lambda 2 is equal to h divided by p1, lambda 2 is equal to h divided by p2. From using these two equations, I can write the here lambda 1 divided by lambda 2 is equal to p2 divided by p1 is equal to 1. Here p1 is equal to p2. The option C is the right answer. Momentum of the two particles are equals. Since momentum is conserved, option C is the right answer. Next question. The de Broglie wavelength of ball of mass 0.06 kg moving at a speed of 1.0 meter per second. The de Broglie wavelength of a ball of mass 0.06 kg. Here the given value, that is mass m is equal to 0.06 kg moving with the speed of, that is v is equal to 1.0 meter per second. The de Broglie wavelength, it is very simple problem. Lambda is equal to h divided by mv. Substitute the values. Lambda is equal to 6.6 into 10 to the power of minus 34 divided by m, that is 0.06. m is equal to 0.06 into 1. 0.06 into 1 is equal to 6.6 into 10 to the power of minus 34 divided by 0.06 into 1, or it is lambda is equal to 6.6 divided by 6.6 into 10 to the power of minus 34 divided by 6 into 10 to the power of minus 2. 6.6 divided by 6, that is 1.1, minus 2 becomes plus 2. Here the minus 2. Now minus 34 plus 2, the answer is 10 to the power of minus 32 meter. 1.1 into 10 to the power of minus 32 meter. Option C is the right answer. And the next question is, an electron and a proton each have a wavelength of 1 nanometer. Each have a wavelength of 1 nanometer. Choose the following. Both will have same momentum. B, electron will greater momentum. Electron will greater momentum. And photon will have greater momentum. D, we can't predict. This is according to the Heisenberg uncertainty principle. According to Heisenberg uncertainty principle, here both will have same momentum. Electron and proton have wavelength is 1 nanometer. If the wavelength is same, the momentum is also same, because lambda is equal to h divided by mv. Lambda is equal to h divided by mv. The wavelength of the electron and wavelength of the photon is 1 nanometer, then the momentum is also same. Both will have same momentum. Option A is the right answer. Then the question number 10 is, the de Broglie wavelength associated with the proton changes to 0.25%. Changes to 0.25%. percent of its initial wavelength. If its initial momentum is P naught, then the final momentum is. Here, the de Broglie wavelength value is. The de Broglie wavelength value is. The de Broglie wavelength is given by, that is, lambda is equal to h divided by p. This is de Broglie wavelength, equation number 1 here, where p is the initial momentum of the particle. Now I change this wavelength. The change in the wavelength is h divided by p square into change in the momentum. As they are given in this problem, the change in the wavelength is 0.0025 into lambda, and change in the momentum is, that is, p naught. Now we get 0.0025 lambda is equal to h divided by p square into p naught, or you can write this 0.0025 is equal to p naught divided by p. From using equation number 1, we get p is equal to 400 into p naught. P is equal to 400 into p naught. Here the option C is the right answer. P is equal to 400 into p naught. Okay, the next concept of your topic is about de Broglie wavelength. It has certain properties. The first property is the waves associated with a moving material particles in motion. Here it is called matter waves, or also called it is de Broglie waves. You know that formula, lambda is equal to h divided by mv, or lambda is equal to h divided by p. P, it is momentum, the product of mass and velocity. And the second property is de Broglie wavelength of wave associated with a particle in motion is given by lambda is equal to h divided by mv. Here h is Planck's constant, m is mass of the particle, and v is the velocity of particle. And de Broglie wavelength of a particle having certain kinetic energy. You know the formula, the maximum kinetic energy is 1 by 2m p square maximum is equal to h nu minus h nu naught, according to Einstein mass energy relation. Here E is lambda is equal to h divided by root of 2m into E. Here m is the mass of the electron, E is the maximum kinetic energy. And the next property is de Broglie wavelength of an electron accelerated through a potential difference of, already you know that formula, that is standard formula, lambda is equal to 12.27 divided by root of V angstrom. And the next property is the de Broglie wavelength depends on mass and speed of the moving particle, and it is also independent of charge and nature of the particle. And de Broglie effects are generally unobservable in case of macroscopic object, because the de Broglie effects are microscopic phenomenon objects. Since their wavelength is too small, they are in the order of angstrom, or they are in the order of lambda is equal to 10 to the power of minus 30 meter. Here the first problem is the momentum of a photon of light of wavelength is 400 nanometer. You know that formula, momentum, that is lambda is equal to h divided by p. P is momentum, then h divided by p is h divided by m into v, or here p is equal to h divided by lambda. H value is 6.63 into 10 to the power of minus 34 divided by lambda value is 400 nanometer, that is 400 into 10 to the power of minus 9 joule second. When you are dividing 6.63 divided by 400, you get the answer 0.016575 into 10 to the power of minus 34 plus 9, that is 10 to the power of minus 25, or can be written as 1.66 into 10 to the power of minus 27 kg meter per second. The momentum of this 400 nanometer wavelength is P is equal to 1.66 into 10 to the power of minus 27 kg meter per second. And okay, the next problem is a hydrogen atom is moving at a speed v. This is the hydrogen atom. Yeah, this hydrogen atom moving at a speed v, and the photon is moving in this direction. It is in the form of E is equal to h nu. It has a certain wavelength, lambda is equal to 100 nanometer. That is 100 nanometer means 100 into 10 to the power of minus 9 meter. And it stops before reaching the hydrogen atom. Then the velocity of this particle is 0. Now find the value of v. Find the value of v. Here the mass of the hydrogen atom. The mass of H atom is, it is in terms of kg, it is 1.67 into 10 to the power of minus 27 kg. But you know the formula. When this photon is moving in this direction, it has a certain mass and velocity, and it has certain momentum, that is mv minus p is equal to 0. Or there you can write this equation, mv is equal to, here mv is equal to p is equal to h divided by lambda, or we have to find the value of v is equal to h divided by lambda into m. Now substitute the values here. H value, that is 6.62 10 to the power of minus 34 divided by lambda value 100 nanometer, that is 100 into 10 to the power of minus 9 into m, that is the mass of the hydrogen, 1.67 into 10 to the power of minus 27 kg. Finally, you get the answer, v is equal to 0.0397 into 10 to the power of plus 2, or v is equal to 3.97 meter per second, which is the desired result. And v is equal to 3.97 meter per second. And the third problem is, a photon is moving at a speed of, here this is the photon, a photon is moving at a speed much less than the speed of light. Photon is moving at a speed much less than the speed of light. Here the speed of light is 3 into 10 to the power of 8 meter per second. Photon is moving at a speed much less than the speed of light. It has a kinetic energy K1 and momentum P1. If the momentum of the photon is doubled, here the relation between, you know the formula, K is equal to P square divided by 2m, or K is directly proportional to P square. If the kinetic energy is K, the momentum is doubled initially. Now if the momentum of the photon is doubled, then its new kinetic energy, the new kinetic energy will be 4 times of its initial energy. And the second point is, a photon with the energy E1 has a momentum P1. If another photon has a momentum P2, that is twice of P1, how is the energy E2 of the second photon is related to E1? Again, you know another relation, that is photon P is equal to E by C, or E is directly proportional to P. Energy is directly proportional to momentum. If the P is doubled, E will also becomes double. If the P is double, E will also becomes double. Here initially it has a certain kinetic energy, but the momentum is double. Now in this condition, if the momentum of the photon is double, the kinetic energy will becomes 4 times. Now you get the answer for the option A, that is 4 times of its initial kinetic energy. Second one, 2 times of its energy. And the fourth problem is, with what velocity must an electron travel so that its momentum is equal to that of photon with a wavelength of 5200 angstrom? Here the given problem is, with what velocity must an electron travel so that its momentum is equal to that of photon with a wavelength of lambda is equal to 5200 angstrom? Here the momentum you know that simple formula, momentum P is equal to h divided by lambda is equal to, that is 6.62 into 10 to the power of minus 34 divided by lambda is 5200 into 10 to the power of minus 10 meter. It is equal to mass of the electron into velocity v. Now here, with what velocity must an electron travel? Then v is equal to, that is 6.62 into 10 to the power of minus 34 divided by 5200 into 10 to the power of minus 10 into mass of the electron, that is 9.1 into 10 to the power of minus 31. Finally, you get the answer nearly about 1400 meter per second, or v is equal to 1.4 into 10 to the power of 3 meter per second. This is the velocity, or in this velocity electron travels. Its momentum is equal to that of photon with a wavelength of 5200 angstrom.